Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important and typical type of question on gravitational field from May-June 2021 paper 4.1. This question is very important because you will see the same type of questions in many past papers. For this question, it is given to us the Earth may be assumed to be an isolated uniform sphere and the mass of the Earth is given. It is also given to us we can assume that the mass is concentrated at its center. A satellite of mass 1200 kg is in a circular orbit about the Earth in the Earth's gravitational field. The period of the orbit is given, that is equal to 94 minutes. For part A, simply we need to define gravitational field. Part A is simply asking us how strong is the gravitational field. I mean, how we can define that, how strong is a gravitational field. In order to understand that, simply we can sketch this one small sphere. Let's say this is our planet. And there is a unit mass, means the mass of this object is 1 kg. We can simply write down the mass of this one is 1 kg. Now gravitational field simply is telling us how much force is acting on this unit mass, and that is the gravitational field. Means we can find out how strong is the gravitational field. We can also write down the small g is equal to F over small m, force per unit mass. So simply we need to write down here force per unit mass. So that's all what you need to write down for 1 mark. If you write down force per unit mass, you will get 1 mark. And this is B mark for this question. This is B mark, means you have to mention this one in your answer. So this is B mark, you will get 1 mark. For part B, we need to calculate the radius of the orbit of the satellite. So it's a great way to sketch first of all, so we can see the clear picture of this question. Let's say this is our planet and its mass is capital M, and satellite is orbiting around our planet, and let's say the mass of satellite is small m. This satellite is orbiting in a circular orbit around our planet. So this is the orbit. The question is asking us to calculate the radius of the orbit. Radius of the orbit means that this is the distance between the centers of these two bodies. Let's say the distance is equal to small r, and this is the radius of the orbit. This is what we need to calculate. Question is asking us to calculate the value of this radius. Now we need to understand, as this satellite is moving in a circular orbit and it is accelerating, because its velocity means its direction is changing all the time, so it is accelerating. If a body is accelerating, it means there is a resultant force, and in this case the resultant force is provided by the gravitational force between these two bodies. So we can simply write down the gravitational force is providing the centripetal force, provides the centripetal force. But you cannot say gravitational force is equal to centripetal force. Centripetal force is just fancy name for resultant force, and it is not a force by itself. In this case, gravitational force is providing the centripetal force. Now we need to understand, according to Newton's law of gravitation, gravitational force is equal to G capital M small m divided by the distance between centers of two bodies square, and centripetal force is equal to mv squared divided by the distance between centers of two bodies. And so they are the same. If you look at this one, the mass of satellite, we can cancel on both sides, and r we can also cancel. So here we left with G capital M, and this is equal to v square, and v is the orbital speed. Orbital speed v, this is also equal to 2 pi r, means the total distance travel in one cycle divided by the time taken, means this is the time period. We need to plug in values of v square, so we can write down this one here now. This is G capital M over r, and here we can write down this is 4 pi square r squared divided by t squared. Because this is v squared, so I just directly plug in these values. So this is v squared. Now we need to rearrange this one for r. So if we cross multiply, we can write down this is 4 pi square r cube, that is equal to g capital M t square. We need r, so we can rewrite here r is equal to g capital M t squared. This is the time period divided by 4 pi square. We need r, so we need here the power of this side. This is 1 by 3. Now simply plug in values, we can find out value of r. G, this is constant and its value is given in data, means the value of g you can find in data. If you just check the first page, you can find out the value of data it is given. Its value is 6.67 times 10 to negative 11. This is constant. If you remember, that's wonderful. If you didn't remember, you can just go to data page and you can find its value. M is the mass of the planet, is capital M. The mass is given, that is 6.0 times 10 to 24. And the time period, this is given in minutes. We have to convert into seconds. We can write down 94 times 60, and this is t squared, so this is square, divided by 4 pi squared. So you can plug in value of pi, and we have to take the cube root of this 1 by 3. If we solve this one, we will get our final answer, that will be 6.9 times 10 to 6 meters, up to 2 SF, and that's the answer. This is how you need to do. This question is very common. Try to understand. Always start with this. Gravitational force provides the centripetal force. Then write down the formula, then rearrange the equation, then find out what you need to calculate. This question has 3 marks. Let me explain to you how these marks will be awarded for this question. You will get the first C1 mark if you have equated gravitational force and the centripetal force. You will get first C mark. And the second C mark you will get if you have substituted the values. And the last mark is answer mark, and this is for correct answer. If you got correct answer, you will get this third mark. For part C, it is given to us rockets on the satellites are fired so that the satellites enters a different circular orbit that has a period of 150 minutes. The change in the mass of the satellites may be assumed to be negligible, means there is no change in the mass of the satellite. For C1, we need to show that the radius of the new orbit is equal to this. In order to calculate the radius of the new orbit, we need the expression from part B. In part B, we have derived that gm t square over 4 pi square, this is equal to r cube. R is the radius of the orbit. Let's divide this one first of all by t square on both sides. If we divide by t square on both sides, we can cancel this t square with this one. Then we simply left with gm over 4 pi square, and this is equal to r cube by t square. If you look at left side, here g is a constant, m is the mass of the planet, that is also constant, and pi is also constant. So simply we can write down r cube divided by t square. This is constant, means the ratio between these two quantities r cube and t square is constant. So we can also write down r1 cube over t1 square is equal to r2 cube over t2 square. T2 means this one is for the new orbit. So this is what we need to calculate. We need to calculate the value of R2. You can also understand like this. Let's say this is our planet. Its mass is capital M. We have one satellite, means the satellite, in this case we have just one satellite. First of all, satellite was at point A. Then the satellite moved to point B. In this case, the ratio between the radius, here this one we are saying is, this is R1, this radius is R1, and the time period in this orbit is T1. Now the new radius is R2, this is the new radius. This is what question is asking us to calculate. Radius of new orbit, and it has to be equal to this one. We need to show that it is equal to this. And the time period for the new orbit is given t2. We have the value of t2. So this is t2. So simply we need to find r2. We can rearrange. We can write down r2. This is equal to r1 cube times t2 squared divided by t1 squared, and we need to take the cube root of this, means 1 by 3. Now we just need to plug in values. R1 in the previous part we have calculated, that was 6.9 times 10 to 6. Cube of this multiply with the time period, means t2. Value of t2 is 150 minutes. We need to multiply by 60. Square of this divided by t1. T1 in part B it was given, that was 94 minutes. So again we need to multiply by 60. Square of that. Then we need to take the cube root of this. If we take the cube root, our final answer will be equal to 9.4 times 10 to 6 meters. And this is what we need to show, that the radius of the new orbit is equal to 9.4 times 10 to 6 meters. This question has 2 marks. The first mark is C mark. You will get first mark if you have written this expression. And the second mark is answer mark. You will get the second mark if you have got the right answer. Let's move on to part C2 now. For C2, we need to state with a reason, means state, and we have to write a reason whether the gravitational potential energy of the satellite increases or decreases. First of all, let's look at this point. When the satellite was at this point, let's say the potential energy of the satellite, that is EPA. And when the satellite was at this point, let's say the potential energy, gravitational potential energy of the satellite is EPB. Now we need to explain, is the potential energy EPB is greater or EPA is greater? For that purpose, we need to understand the gravitational potential energy. Gravitational potential energy is simply is equal to G capital M small m divided by R, and R is the distance from the center. If R is greater, EP will be greater. The reason is that because if R is greater, this will be less negative. When this is less negative, it means EP is greater. EP is 0 at infinity. If we look at EPB, this is less negative. This is less negative value as compared with EPA. This is more negative. So we can simply write down this one is more negative. It simply means that in this case, EPB means the gravitational potential energy of the satellite at B is greater than gravitational potential energy of the satellite at A, because R is greater. If R is greater, it means gravitational potential energy is less negative. So that's the reason. First thing you need to write down increases. We can simply write down gravitational potential energy increases. Second, we need to explain why increases. We can simply write down the reason is that because the separation increases. We can write down separation increases, or you can say the distance from the center of the planet increases. And this question has only 1 mark, and that mark is B mark. For this part, we need to determine the magnitude of the change in the gravitational potential energy of the satellite. First of all, let's try to understand this with the help of one sketch. Let's say this is our planet and its mass is capital M. Satellite was at the beginning at point A, then satellite moved to point B. When the satellite was at point A, let's say the radius of the satellite was R1. And when satellite moved to point B, let's say the radius of the satellite, this is R2. We can also assume that the gravitational potential energy of the satellite when it was point A, let's say this is GPA A, and when the satellite is at point B, its GPE, gravitational potential energy, is GPE sub B. Question is asking us for the magnitude of the change. It simply means the change in gravitational potential energy, GPE, that is equal to gravitational potential energy of the satellite at point B potential energy at point B is greater minus gravitational potential energy of the satellite when it was at position A. Now we also need to understand GPE. This is equal to negative G capital M. This is the mass of the planet, and small m, this is the mass of the satellite, divided by the radius of the orbit. This is R2. When it was at position A, the radius of the orbit is R1. We need to write down this negative sign is very important. This is divided by R1. Now you can see here, if we multiply with negative sign inside, we can write down G capital M small m. Here we multiply, so this will be plus G capital M small m over R1. Now from here we can take G capital M small m, we can take common, then we can write down this is 1 over R1 minus 1 over R2. Now simply we need to plug in values of G, capital M, small m, R1 and R2. Capital G, this is 6.67 times 10 to negative 11, and the mass of our planet is 6.0 times 10 to 24. Mass of satellite is 1200 kgs, and the radius of the orbit when the satellite was at point R1, we have that was equal to 6.9 times 10 to 6. When it was at point B, we have calculated that was 9.4 times 10 to 6. Now simply we need to calculate. If we calculate this one, our final answer will be 1.9 times 10 to 10 joules, and that's the answer. That is the change in gravitational potential energy of the satellite when it moved from point A to point B. Let me explain to you how marks will be awarded for this question. This question has 3 marks. The first mark is if you have written these formulae, you will get first mark. If you have written the formula for gravitational potential energy, this is C mark, first mark. And the second mark you will get if you have substituted these values, you will get second C mark. And the last mark is answer mark. If you have got the right answer, correct answer, you will get the last mark. If your answer is not right, but you have written these steps, means you have written this formula, you have plugged in values, you will get 2 marks. So it's good to write down all the steps and show your working.